Right, hi everyone. So I hope everyone's awake. We have a lot of ground to cover. There's clearly a huge amount involved in developing an LLVM backend. I've gone back and forth a few times. I did a test version of this and exactly how to structure it. So it's obviously in a 45-minute talk, we can't cover everything, but I hope to give a useful sort of slice of what's involved in developing an LLVM backend. Hopefully have a broad enough coverage that everybody can get something out of it, regardless of your level of experience of LLVM. And I'm trying to kind of carefully pick out the areas where we want to go into detailed examples, and then there are other aspects where we'll just try and talk over the sort of high-level idea in order so that you have, I guess, a mental model of what's going on, which will then be useful if you go out and go and read further documentation, read the code, or try and start hacking yourself. So in terms of hacking, I should mention we have a coding lab tomorrow, 2 p.m. to 3:30 p.m. I think it's in the room down the way where the round tables are. So it's a new sort of trial for this LLVM dev meeting as a different way to try and get people doing some hands-on work. So you should have had an email about it via the event organizer, I think last week, pointing to some instructions on how you can get a build of LLVM checked out. So hopefully you can pick up a lot of stuff today, and then you can try and put some of it in practice tomorrow in the sort of round table at your own pace, working through the example problems. And so in terms of myself, I'm the upstream code owner of the RISC-V LLVM backend. I also authored a lot of it. I've been working with LLVM backends for about 8 years now. Prior to that, I was working on outer tree backends in a research context. And one of the things that I've been keen to do from the start of the RISC-V LLVM backend development was to try and do it in a way so that other people can learn more about writing backends, and so it's easier for other people to make modifications as well. Because one of the ideas about the RISC-V instruction set architecture is that it's very, in terms of a licensing model, it's very easy for different vendors to add their own extensions. And so it'd be nice if, when they go and do this, it's not a massive or an unreasonably large undertaking to go and add support for those extensions to the compiler. So I'm just going to give a very brief background on the RISC-V instruction set, which we'll be talking about. You don't need to be familiar with it or the details. All you really need to know is that it's a modern RISC instruction set. You might be interested in the fact that it's designed as a extensible open standard. It's worth knowing that it has variants with 32-bit, 64-bit, or 128-bit register length, register width. It's designed so that you have a very small, minimal base instruction set, which contains less than 50 instructions, and then there are a series of standard extensions, such as adding support for multiply and divide, atomics, single and double precision floating point, and this is what enables you to have different variants, either for very deeply embedded microcontroller applications or Linux-capable machines. And of course, we want our backend to support all of those. For more information, check out risc5.org, and there are several RISC-V themed posters at the conference. So there's a poster tomorrow about fuzzing the MC layer, so the assembler and disassembler, and another about support for the compressed instruction set. And I should also briefly say, so in the RISC-V world, we refer to these rather, I guess to outsiders, opaque strings to refer to different instruction set variants. So you'll hear RISC-V people talking about RV64 IMAC or RV32 IMA FDC. And that's just a shorthand way of referring to the base instruction set, so RV32 or RV64, and then which of the standard extensions are supported. So I'd mention that, as I'm probably going to start spitting out those abbreviations. So we want to learn something about how an LLVM backend works. We want to figure out how we can start to do something useful in let's say, a new LLVM backend. So taking a step back, let's look at a very simplified view of the compilation flow we might want to support. So firstly, code gen, traditional. We have, let's say, C is our input language. This gets lowered to LLVM IR, obviously through other stages, through AST and so on. We have something called the Selectiondag, which we'll talk about in much great detail later on in the talk. This gets converted to a machine instruction representation, then finally to an MC-inst representation, and then we generate our ELF object file. Then look at the assembler, which we may also want to support in our backend, and that we take the assembly as our input. This gets parsed. We generate MC-inst, which are machine instructions which we are able to encode, and we spit out the ELF file at the end of that. And so if we're sure of the fact we want our backend to support integrated assembly and disassembly, then actually it's a pretty reasonable starting point to start with this MC-inst to ELF level. So we can actually start by completely ignoring code gen and just looking at adding necessary support for the assembler and disassembler. And I've actually found that to be a very productive way of building the backend up, as it gives you a very solid base for you to work with. You can build up, you can sort of get that, the whole assembly part in the bag, and then go and add code gen on top of that. So that's exactly where we're going to start. So first of all, I'm just going to give a brief overview of how we're going to attack this. So initially, we'll look at how you actually specify what an instruction is to LLVM, what its encoding is, what the assembly syntax is. But once we've done that, you'll also want to describe its operands, so its registers or immediates. We'll need to write some amount of support code for the assembly parsing, and then there's LLVM provides a lot of infrastructure for you, but you've got to go and implement the code to actually hook it all up. We'll then talk a bit about the sort of testing approaches you might use, as well as where you can go and find out more information about how all this works, and what to do when things don't work first time, which, at least with my experience with LLVM development, or really any development on a large project, things tend not to work first time. So this is an exploded definition of a single instruction. So this is not what you typically write for every single instruction, but I'm trying to demonstrate kind of the various components in a sort of single combined form. Now, this is in a domain-specific language which LLVM uses for a range of things. So even if you've never touched a backend, you might have encountered table gen for options parsing or something else. I'm not going to walk through a detailed language definition of table gen. I think for the most part you'll be able to kind of follow my examples and see what's going on. Essentially, you use it to define records. Each of these records has fields. They may have they may derive from a superclass, and through this you're able to quite productively describe information about instructions, about patterns matching those instructions, and a whole bunch more. So let's kind of decompose this very verbose definition. If you want to go and have a look at that, you can go have a look at it in the lib target RISC-V directory, where basically all the RISC-V backend lives. So first of all, encoding. So the bits I've highlighted in bold, they're all related to specifying exactly how our add instruction should be encoded into a 32-bit wide integer value. So you can sort of soft fail is that's a requirement for, I think, the disassembler. We can sort of ignore that, but the inst field, that's what's going to describe our eventual output, whereas the RS2, RS1, and RD fields, these are obviously things which these are elements which we need to encode in our output instruction. So the RD is a destination register, RS1 and RS2 are our two register operands, and then if we look at these definitions here, these specify the offsets within our 32-bit output that we need to fill in. So I added a little comment here. So these ones which are constants, those constants just come from the instruction set definition. So it's part of a definition that an add, it has this field is always all zeros, this field is always all zeros, and this opcode field always has this value. And so all we're doing here is specifying that these fields, which need to be filled in somehow, which the assembly pass will need to fill in, or the code generator will need to fill in, they get stuffed into the instruction in these locations. Right, So that's the encoding. As I just said, we need to figure out how to take something from either the code gen pipeline or through parsing an instruction and then, parse it and then stick it into one of those fields. And that's what these definitions do. So these define really very simplistic patterns for the output of the output and the input. So in this case, we have a output is a target register, RD, and the inputs are, again, a single input, the RS1 GPR and RS2. And finally, we need the assembler to understand how to actually parse this. So we know that our add instruction is spelt with the add mnemonic, and it's the add mnemonic followed by the destination register, comma, and the two operands. And with that information, the LLVM MC layer, so machine code layer, which handles the assembly and disassembly, will actually generate a large portion of the code for you in terms of actually parsing that add operation and checking whether you've specified the correct registers and that sort of thing. Now, doing this for every instruction, and every instruction is going to be incredibly verbose and tedious, we can make use of the features in table gen to try to reduce duplication. So we can introduce a superclass, which in this case, which describes this sort of instruction in the RISC-V ISA. So there are a whole bunch of instructions which have this form where you have one destination register and two input registers, and we can have a class which describes what they look like, and therefore we don't need to repeat this for every definition. And if we can even define another class which defines the case of a ALU type operation and reduce duplication substantially. So this is at least all that the MC layer needs to know about every register ALU operation in the base RISC-V ISA. So I guess you'll notice from the table gen definitions there that this is a single record definition which implements this class and passes in these parameters. And I guess it's a design choice that different backends will make in terms of exactly what level of what sort of classes and multi-classes and other fancy table gen features they use. There's clearly a trade-off between reducing duplication, which is nice. One of the benefits of this description is that it's very, very easy to cross-reference it against the ISA manual, double check that it's right. But there's a trade-off in terms it can be a little bit more, someone who's just reading it and wants to look at what's really going on, you might have to end up sort of manually piecing it back together in your head to try and build this. Or alternatively, you actually, as I'll mention in a few more slides, you can actually just look and see what the records that were ultimately generated through the table gen process. So that was an add. We might also want to describe other sorts of operations, such as register immediate. And in this case, so previously, the previous one, we just had GPR operands. In this case, we have an immediate. So I've specified a signed immediate 12-bit, which is the maximum which can be encoded in the RISC-V add instruction. But of course, we haven't really gone into where this GPR definition comes from, and indeed where this SIM12 definition comes from. And so we actually need to take a step back. We sort of started with the meat of what we're trying to do, which is describe how to specify the encoding of instructions. But in order to do that, we need some level of support infrastructure. We need to describe exactly what these operands are, what is a GPR, which leads us to want to describe the registers which our target supports. And this actually, there's a whole bunch of stuff which you probably don't really need to follow here. The main thing to take away is that you describe, there is a class which you can derive from, the register class, which describes the name for the register. So for instance, in RISC-V, the register which is encoded as 0 can be spelt as X0, or alternatively, there's a ABI name, so it can also be spelt 0. This will be used when we implement the assembly parser in order to, and will result in an automatically generated method which will parse your registers. And once you've specified each of the individual registers, they need to be grouped together in a register class, which is, so this is our GPR definition, which we referred to here. So as specifying this, which is so this is using a table gen feature in order to add all 32 registers at once. This means that any of the registers specified here will be recognized, but if you specify something which isn't a recognized register, let's say X33, you'll get an error generated for you by the parser. Now, immediate operands are somewhat, again, you need to describe what exactly it means to be a 12-bit signed immediate. In this case, you specify that we have an operand, and the main bit you need to care about for the parser is this parser match class field. That contains a ASM operand class, which has various fields which indicate which methods are going to get called in order to validate it, in order to add it to the machine instruction that we're building, and also what we're going to do, what type of error to generate if it fails to, if we get something unexpected. So in this case, there's going to be the fact that we're defining a sim12 as the name. That's going to imply that a validation method is going to get called in our assembly parser, which we're going to have to go and implement ourselves. And also that our assembly parser is going to need to handle invalid sim12 as an error condition. And that's pretty awesome. So with that, with those definitions, that actually gets you quite a long way there in terms of being able to parse real input, but not all the way there. You have to implement some logic yourself. So it's going to generate methods for us which are going to determine whether a register name is correct or not, that are going to determine whether the ABI register names are recognized or not, and which are also going to take a parsed instruction and then determine whether it's valid or not. So say taking suppose that somebody input an add with 2 immediates, that might go through the parser, but then match instruction impl, which is auto-generated for you by table gen, would then fail because it doesn't match any legal instruction. So in terms of things you have to implement a class to represent those operands as they're parsed. In our case, RISC-V operand, which indicates whether it's a register, whether it's an immediate, and also has those methods I mentioned, which get called via, which are named according to this ASM operand class in order to check whether it actually fits that definition. So checking whether your integer really is a signed 12-bit immediate. And on top of that, you need to implement some diagnostic handling, which is an important part of the assembly parser, as well as some top-level logic for actually parsing an instruction or parsing a register. So there's a code example here, which I'm just going to look at very briefly. You don't need to look at all the details. The key point is that you interact with an assembler Lexa. We can check what the current token is. We can peek at the next token, and we can consume tokens as we need to. In this case, all this is doing is, so at the point the parse instruction is called, it's already grabbed the token for the instruction name. So we stick that to a list of operands that we're building. I guess operand is a slight misnomer. We'll then cycle through, try and parse each additional operand. As there are commas, we skip those, parse the next operand until we get to the end of the statement. So you'll notice that there's no sort of semantic checking at this point. So the operand could be, as I said before, you could have 2 immediates for an add. The semantic checking will come later. That's a sort of general model that the assembly parser uses. And as a warning, as false in the parser for both, I believe, the Clang parser and in the MC layer assembly parsers indicates success. there's a discussion recently about sort of changing this, as it's which would be nice to do if anybody has free time and wants to go and write that patch. That would be really nice. Right, so that gives us the core of the logic needed to pass instructions. As with most things in LLVM backend development, you're relying on a lot of target independent code. You're helped a lot by table gen, and for the most part that's really useful, but it can mean that you can spend quite a lot of time just trying to figure out which bits you need to piece together and where they need to go. And also what the minimum you actually need to implement is. One of the it's easy to look at an existing backend and see the tens of thousands of lines of code that they have, and copying and pasting that in order to start your own development for a new backend is probably not a good starting point. I hope that looking at the sort of RISC-V patches I built up might be a useful way if you're trying to start a new backend. I know that a few of the backends people have been talking about proposing recently have followed that sort of approach. So there's some extra stuff that you'll need to do in order to actually recognize, in order to hook up your assembly parser to something useful. You need to register it with the sort of internal infrastructure for registering a target. You need to support the triple, i.e. RISC-V 32, unknown Linux, or what have you. You need to define whatever architecture-specific definitions there are for your platform, such as relocation numbers, and then implement. There are a few sort of helper classes which need to be implemented. RISC-V MC ASM info mostly contains sort of simple things such as which feed into the target independent assembly parser, things such as what the comment delimiter is. These two classes are mostly for handling fix-ups and relocations, which we're probably not going to have time to go into in any great detail in this talk. And then RISC-V MC code emitter does a very important job. That converts your MC int, so these instructions which we produce from the assembly parser, and then encodes them. But there's effectively no code you need to write here other than implement the class and ensure that it includes the table generated code that actually does this. And very important part, the test infrastructure, which we're going to have a quick look at now, because you can spend as much time as you like actually going and trying to get this stuff to work on a few simple programs, but you want to integrate a unit test into the tree so that you can ensure that it continues to work as you refactor your backend and as you add new assembly features, and the same for code gen as well. So in the LLVM world, there are two tools which we rely on heavily. There's file check, which is effectively a helper which will check for expected patterns in the test output, and there's lit, which is the LLVM test runner. There's not much I have to say about lit other than you just need to know that that's a tool that you're going to need to run you'll need to execute to run your unit tests. But all of your tests will make use of file check, as we're doing here. So these run lines, they're interpreted by lit. They specify what needs to be executed in order to actually run this test. And then we can see that we use LLVM MC, which is an LLVM tool which gives you an easy way to access the MC layer. It'll just in this case, take your assembly input, and in fact, this is just doing a sort of no-op output. It'll parse it, and then it'll print your assembly input straight back out again. This then gets passed through to file check, which is going to go through each of these comment lines, and it's going to check that these expected values actually occur in the output. And so in this case, it's structured so it does a round trip. So I have one check which is doing the parsing the assembly, printing out again, so checking that that does something sensible, i.e. our assembly printer does something sensible, but also parses the assembly, generates an object, and then disassembles it again in order to ensure that we get the same output. And you can just build this up throughout the whole backend, and it's completely feasible to do this without, in fact, that's a better version of that slide. It's completely feasible to build up an entire backend with complete assembly support without doing any work on code gen whatsoever. I should also say it's also really important to check for invalid inputs as well, as a lot of the bugs you'll encounter come from invalid inputs silently being accepted and incorrect code being generated. So that's also an important part of the testing task. Right, so in general, there are a few places you might want to go for more info. LLVM documentation and mailing list, the RISC-V, so I sort of maintain a outer tree version of the RISC-V LLVM patch set, which I keep updated as I can in order to sort of show if things were implemented perfectly first time, this is what it would look like. It's in due for another, it could do with another rebase. I've had less time to do it since my son arrived, but hopefully soon I'll have a bit more time to update that. I'll highlight that it's really, really useful for any of this development to get used to reading code for other backends. A lot of the times when you encounter a problem, there won't be documentation or maybe even a mailing list post which specifies exactly what you need to do to solve it. But if you understand something about other targets, you might be able to find how they've tackled a similar problem and then apply that to what you're doing. So I think for any LLVM development, getting used to reading code, both looking at other targets, but also, as I mentioned, a lot of the work you do is where you're filling in often relatively small callbacks, which then get called by some target-independent driver. Often you'll want to sort of go up a level and try and work out, what this sort of the code that's driving the process is doing. So getting the confidence to be able to do that really helps. And I guess related to that, checking commit logs and git blame can also give useful insight. Finally, related to that, there are a number of sort of standard definitions of things which were referred to, such as, you might wonder previously, I think I had an example of specifying a register that extends the register class. Well, what is a register? If you want to go and see the definition for that, then you can look at the standard definitions in this file, include LLVM target.td. You can also look very specifically at the MC layer. So check that file I mentioned. You can also run this command line in order to have TableGen spit out everything for every record that was produced by your input, which can be useful as a sort of sanity check and also seeing what's going on. And particularly useful given that sometimes TableGen will infer some properties. So it's quite often handy to check that, to double check that it's inferring what you think it should be inferring. And also going and looking in your build directory and looking at the files which get spit out is also useful. Because TableGen's model is that it passes its input, it produces records based on that input, but then it has a series of different generators, or I guess you'd call them like backends, which then which will spit out generated files for different purposes. In this case, for the register info, instruction info, and the code for matching in the assembler. Right, so that was a very whirlwind introduction to the MC layer, which should sort of get you started with your backend development. And clearly for any new instructions that you introduce that you want to support in the assembler, you'll want to go and sort of follow, do something like I've just described in order to support them. But for many people, the exciting bit is code gen, which is taking our LLVM IR and trying to produce select instructions based on it. So we're going to sort of step through a few simple examples of that. And we've gotten almost halfway through without an LLVM IR example, which is quite a long way from an LLVM talk. So I thought I'd better stick one in about now in case people start worrying that start missing it. We're going to look at a few very, very simple examples in the simplest possible inputs that you might want your backend to handle. So two functions which simply return constants, and then a function which does an add with variable arguments, and a function which does an add with a constant argument. And we're going to look at how you specify instruction patterns which will handle those inputs, as well as the associated infrastructure that you'll need to handle things. So we'll look at instruction selection patterns for those. We'll look at this Selectiondag thing, which I mentioned earlier, which is actually, although there's a huge amount of target-independent code that you're able to harness through LLVM, as a backend developer, you'll actually, in my experience, find a lot of time scrutinizing this whole process, because a lot of the work that you do in the backend is implementing target-specific hooks or otherwise influencing the Selectiondag process in order to influence the input to the sort of final instruction selection phase. We'll talk briefly about calling convention support and lowering returns and formal arguments. Look again at testing for code gen, debugging, and maybe if there's time, have a brief look at C++ implemented instruction selection and maybe a slightly hairier example that might pull everything together. So before we go further, I think it's worth zooming out just a little bit and talking about what the Selectiondag is in LLVM. So most of you will have been, I assume probably everybody has been exposed to LLVM IR before. So we know that we have LLVM IR as our input and we want to produce assembly as our output, so selected machine instructions. And the Selectiondag is what helps us go from point A to point B, and it's kind of an iterative process. So when we're writing patterns to try and generate our chosen instructions, they're not written directly against LLVM IR because IR doesn't have target-specific restrictions about legal operations, about legal types, and so on. Through the Selectiondag lowering process, we move iteratively closer to native operations which our target supports. So this works first in Selectiondag Builder, which does mostly a very simple job of visiting each IR instruction and generating an equivalent Selectiondag node for it. This then goes through the DAG combiner, which are a series of optimizations which try and capture sort of redundant operations, and it builds up a whole bunch of logic about tracking known bits and all sorts to try and produce eventually produce more efficient code. It then goes through the first legalization step, which is legalizing the types. So let's say you're targeting say a microcontroller doesn't have any support for floating point. Your LLVM IR might have floating point types in it, but the legalized types pass will go and convert those to a legal type, let's say 32-bit integer. These legalization passes, they're structured in a way that they do something fairly simple and naive. So after the legalization phase, you want to do another call of the DAG combiner in order to sort of clean up any messy operations which we generated. Then there's a second legalization phase. So once the types are legalized, there might still be some operations which aren't actually legal. So maybe some floating point operations aren't legal on the target, they need to be lowered to intrinsics, or maybe your target has particular bit manipulation, doesn't support a bit manipulation instruction which is recognized in both LLVM IR, maybe as an intrinsic, and in the Selectiondag node, but there's no native instruction for it, so we'll have the target independent code expand that to something which we can directly match. There's then instruction selection, which is this important part of matching patterns against your Selectiondag and producing a representation of the selected machine instruction. Then a scheduling step, and then these get converted to a machine instruction for the next phase. And I think what's really important to point out here is that isn't the end of the compilation process. You can write your backend without probably caring too much about exactly what goes on after this, but at the point that we're generating machine instructions, this is actually pre-register allocation. So there's all that to go on, and there's also both target independent and potentially target dependent machine function passes, which could be doing things such as machine level common subexpression elimination, and well, I guess whatever you might dream up for your target. So although often when you're bringing up a backend, you might focus very heavily on this selection phase, it's worth remembering that there's still quite a lot of work that goes on afterwards. So the first example that we had up there was a trivial function which was just returning a constant immediate, and it's returning a fairly small one, which is handy because it's a constant immediate which we can match directly to a instruction. So the core of this is this pattern right here. So on the left-hand side, this is the Selectiondag node that we want to match. So this is anything which matches this sim12 predicate, and we want to expand that to a add immediate with 0 as the source and with the immediate as the other operand. So this is clearly just going to load that immediate into the target register. Again, we had sim12 was defined in a way that made sense for the MC layer. We can make use of the table gen support for multiple inheritance to specify that sim12 is also an imleaf, which is a what's called a pattern fragment, which is really just a which basically is something with a predicate which we can match against our Selectiondag. So in this case, a predicate is that it is the immediate value is a signed 12-bit immediate. So as long as that is true, this pattern can match and we can generate this output. So you might be wondering how you know, how you can look up the definition of imleaf and that sort of thing, and that's where you want to go and look up this include LLVM target selectiondag.td. Now, for 32-bit immediates, it gets a little bit more involved. So let's start at the bottom with the core instruction selection pattern. In this case, we have a 32-bit immediate as our input, and we want to, so in RISC-V, that's handled with two instructions. You have LUI for load upper immediate, that handles the top 20 bits, and you have the add-I, which handles the bottom 12 bits. Now, because the immediates are sign extended on RISC-V, you have to do a little bit of mutation for the input, which is where this logic comes from, though you don't need to worry too much about that. Just trust that there is a little bit of bit manipulation you need to do in order to make sure that you get the same value at the end of it. And so in order to, so you'll note we have a single input and we need to split it into its two components. And that's where these two definitions come in. These are transforms on the input Selectiondag nodes, which will split out the top 20 bits, appropriately mutated top 20 bits, and the bottom 12 bits. And so you can see generating this was super easy, this was a little bit more complicated. We're now getting back to something which is a little bit easier again, which is just handling a simple add. So again, we have a pattern which has the input pattern is the Selectiondag node we want to match. The output is the machine instruction we want to generate. So if we have a add which has two registers as its inputs, we want to produce an add instruction. Simple as that. And similarly for add immediate, if we have an add which has a register operand and a 12-bit immediate operand, we can generate this as the output. So it might be worth thinking about what would happen if we hadn't specified this extra pattern, which is, I guess, if you imagine other operations that our backend are going to encounter, could be quite common, because we have add immediate is present because it's very common in input code, but there are other operations that only have register forms. And so in that case, that's when so if we hadn't specified this and we encountered an input Selectiondag which had an add with a immediate operand, the instruction selector would just go back to the immediate materialization code. It would load it into a register for us, and then we'd be at the point where we can match this register code, match the add with two register inputs. And yes. Okay, I thought I had it right. Yeah. That's fine. Right, so using patterns like this, you can basically support all of the register or register immediate ALU operations in RISC-V or really any target in a pretty straightforward fashion. But then there are other instruction forms which are more complex to support. And I should say there are multiple ways of handling, say, load store instructions. Some backends might decide to define a complex addressing mode and then match that. In the RISC-V case, I've tried to keep it so that the instruction definition matches the architectural ISA definition very, very closely. So rather than saying that a load takes this complex single operand, I say that a load takes a register and it takes an immediate. And we don't need to go through in great depth what's going on here, but effectively we're introducing a new table gen feature, so we can define this multiclass, which means that if we stick in these parameters, it will do all of these definitions for us, and that makes it much simpler for these cases, much simpler because we can just say if you encounter this sign extended load, then generate all of these patterns for it, which end up producing this load byte instruction. So the patterns need to handle the different variants of input that you might have. So you might end up with a Selectiondag input where you have a single register operand, you have a register plus an immediate. There are cases where, because your load, so a register plus an immediate, and this is immediately here you'll see that we have a more complex pattern because we have a load operation, and then it has a branch in the acyclic graph, so it has a child node which we also need to match against. So this is a case where you have a slightly more complex address generation. You have a base address plus an offset, and we want to match that to our load operation because, of course, our load operation is a base address plus offset. Some of these are for more complex reasons. So the address FI is to handle support for frame indices, which is related to handling stack spills or other things which are on the stack. There's much more to say about that, but I won't say that here. If you look at the GitHub repo I mentioned, in the docs subdirectory, there's a more sort of narrative description of the patches, as well as looking at there's sort of individual patch where I added frame index support, which you could look at that if you wanted to get more info there. So this is an example from sort of debug output, which is indicating what's being matched in the selection. So this is a textual description of a Selectiondag, and ultimately this is what we're trying to match. We have an add. It adds this to this constant, and we've written a pattern just here which will match against that. Yeah, so I think I've covered most of that. There's extra code that you'll need to implement in your backend to handle the logic that you need. I mentioned that the Selectiondag goes through these legalization phases, these combine phases. All of these work based on knowledge of your backend, and you need to imbue the target independent code with knowledge with exactly which operations need to be expanded, which ones are legal, which ones aren't. So you'll do that in RISC-V ICEL, in your target ICEL lowering.cpp typically. So in the constructor, that will do things such as register specify what the register class is, that indicates which types are legal. So in the 32-bit RISC-V case, there's a 32-bit register class, so I32 is legal. If you have floating point support, you'll have floating point registers indicating that F32, so 32-bit floating point operations are legal. And you'll have a whole bunch of code to specify, let's say, whether multiplies are natively supported or whether you want the target independent code to expand them out to, say, in trivial cases, to something straightforward, or else a call to a helper function. You'll also need to implement support for lower formal arguments, lower return and lower call, which are responsible for assigning locations to arguments based on the calling convention. So say that your function takes a 64-bit integer as its input, and they're responsible for doing the right thing regardless of whether it's that's passed in, say, maybe a register or a pair of registers or on the stack, or split between registers in the stack, and that has to copy them to a register so that the rest of your lowering code is actually able to access them. And there's also more support code that's needed that we won't go into in any great depth. Testing for this is handled, again, using file check, run using lit. For me personally, I make very heavy use of this update LT test checks helper script. What that allows you to do is to auto-generate these check lines. So these check lines check the generated assembly, and as you're using Git is tracking the values of those lines. Simply updating that whenever you notice a change and doing a git diff can be very productive. I'd say that it's worth highlighting that all of the in-tree unit tests involve no native execution at all. They're simply checking that the output is what you expect. So for any, you'll clearly want to augment them with tests from external test suites, maybe the GCC Torture suite or a commercial test suite or target applications. There's, I guess, some general advice here on for debugging. You're obviously free to use whatever debugging tool that you want. LLVM has some helpful infrastructure for printing stack traces and that sort of thing. In the specific case of debugging instruction selection, you can ask the LLVM compiler to spit out this long debug trace, and then you can go and cross-reference these indices against the code that was generated for the pattern for the instruction selection, and you can sort of follow why it is that the pattern you expected to match isn't actually matching. There's an example we can look up later of how to handle instruction selection in C++. And this is simply doing the exact same pattern that we did for add immediate, but implementing it in C++. Sometimes very, very complex things that you want to match that you can't specify within the limits of table gen. Clearly, this is a good example of why table gen is helpful, because it means that you don't have to write this for every trivial instruction. There's a hairier example in terms of how we added support for the double precision floating point with the SoftFlow ABI, but I think we don't have time to go through it in any great depth, so you're welcome to catch me to talk about it afterwards or tomorrow. So this has been a whirlwind and very selective tour, and there's clearly much more that you'll want to learn if you're interested in getting involved in RISC-V LLVM backend development. I could definitely recommend checking the LLVM documentation, the split out patch set I had. Also look at the previous tutorials they've had on backend development. Both of those have taken slightly different approaches. Some have gone into greater depth on other parts of backend, which may be useful for you. And also definitely come along to the coding lab tomorrow. The prerequisite is that you have a checked out built version of LLVM for you. So if you check the link for the instructions, which was sent out last week or is available there, that should tell you how to do that. And then I have a basically sort of worksheet that steps you through trialing some of the things which I mentioned. So adding a very simple instruction pattern and seeing how that works in the back end, as well as there's quite a range of tasks really, so it can sort of scale up to depending on your level of experience. And with that, I think I'll open the floor to questions.
So we do have time for a few questions. If you want, then just raise your hand and I'll bring the mic to you.
Hi, Sitaram here. So do you suggest that we start with the assembly part first, or we start with the high level IR too?
So I found it useful starting with the assembly level first, given that I knew that it meant that there was a sort of it's easier to write and test than the cogen component, and it gave a sort of solid baseline that I could build everything on top of. But I mean, some people, so of course there are a number of targets which don't have any assembly support in LLVM. They make use of an external assembler, so that's a completely valid design choice as well. So it's up to you. I mean, one thing that I've done in the RISC-V backend, which I might not mention explicitly, they actually split the instruction definitions from those instruction patterns. So if you look at a number of other backends, you might see that you have in your definition of the instruction, as well as specifying aspects for assembly parsing and encoding, it attaches a pattern directly to it. We had some discussion about it in the RISC-V community, in the LLVM community as well, and decided that we liked the idea of sort of splitting out the instruction patterns elsewhere in the file so they can be sort of ordered logically in a sense that makes sense according to what's being matched in the Selectiondag, and because it didn't seem to make sense to just try and, I guess, munge everything together. But yeah, the answer is either. Either is a valid approach. I found it useful to start from the MC layer, but different projects might have different requirements.
And you can give an instruction cost as well?
Yes, so there's a whole bunch of things that I haven't gone into, which will affect scheduling, which will affect, as you say, the relative cost of instructions. You can specify that some patterns have a higher cost, so they're less likely to match. There's a range of different ways that you can sort of influence behavior.
And where do you do instruction fusion?
Instruction fusion, as in? Do you mean optimizing for a target microarchitecture that does?
So there may be one instruction that implements a whole piece of the DAG or something.
Yes. Oh well. So there are different edges of fusion. So if you look at the example of load, for instance, here. So there we had a pattern which was a load and an add. So that's taking a load and add operation and lowering it to a single operation. So that I think that might be what you're referring to. There's also another concept. So some microarchitectures have support for at dispatch time fusing multiple instructions, and so there is also some infrastructure you can hook into which allows you to try and tweak it so that instructions which are candidates for that dispatch time fusing are placed together.
Any other questions?
Question to RISC-V backend. Do you plan to support fast ISL or global ISL?
So I'm watching global ISL work with great interest. At this point, it seems like there's probably not a strong argument for implementing fast ISL for a new backend. So I would like to support global ISL. I haven't put much time into it. I'd be very interested in seeing the latest global ISL update talks.
I guess this is only tangentially related. There is a number of cases in which we need to do binary analysis, from the outputted object and reverse back to do analysis, and not every time we can compile to LLVM IR to do the analysis on the IR. From your experience working in the backend, how feasible do you think working with that infrastructure from the disassembler and the pattern matching as is described in the framework you showed, could we use to analyze? How feasible you think it would be to write code analyzing those data structures from the framework as it was described?
So, but in reverse, so disassembling it. So that is challenging. So there has been some work on it that I can't speak to with personal knowledge. So if you look at, I think that there are probably, hopefully one of the authors is around at the dev meeting. There have been a few of the Trailer Bits and Quarks Lab and those sorts of companies. There have been projects from those quarters which have looked at adding LLVM infrastructure for binary analysis. So I'd look at those projects. I think there's much more to it than just hooking up into sort of the existing infrastructure.
We have time for one more question.
So I was wondering, what do you think the best way to discover new things you can do in the backend is? So I've been working on the WebAssembly backend for a couple months now, and just the other day I found out about this instruction relational mapping thing you can do. And I just found that because I happened to be perusing the right bit of documentation. So what do you think the best way is to find out these little useful features that aren't so prominent?
Yeah, well, I guess it's partly code reading. Partly following commit logs and that sort of thing. One of the reasons I started LLVM Weekly was because I found that I was reading commit logs anyway, and I thought, well, I might as well, I'm already making notes of what I'm finding. I might as well put it in an email so other people can benefit. So it's I try and highlight sort of interesting things which are add to other backends. So yeah, in the same way, if you mention often, I'll discover something, I'll say, oh, PowerPC added something, I didn't realize you could do it that way, or I did something similar, but it was about a few times longer, I'll steal that from them. So yeah, trying to follow what's going on in other backends is useful, and beyond that, it's, I guess, happenstance, or I guess encouraging people to try and document, when there's new infrastructure that's useful, trying to encourage them to document it. There's definitely a challenge for writing a backend in terms of like all of that DAG combined infrastructure I mentioned. If you go and look at the huge list of target hooks that you could implement, you've got no way of knowing which ones are actually worth it for you. And that tends to get worse with time because people want to add in new hooks. Well, I want to add in some new hooks for RV64, and then that's going to add to the problem. So there's definitely a bit of a discoverability problem in terms of knowing sort of what the best cost benefit is for those sorts of things.
So I think Alex would be happy to answer further questions later. So for now, let's thank him again.
Thank you.